G'day! Here's my favorite number tree of all time. It's actually a tree of fractions called the Calkin-Wilf tree. It was presented by two mathematicians, Neil Calkin and Ebert Wilf, back in the year 2000. And it goes as follows. You start with the fraction 1/1/1. And every fraction of the tree has two children, a left child and a right child. And they're created as follows. Given a fraction a over b, its left child will be the fraction with the same numerator a, but denominator a plus b. And the right child is going to be a fraction with the same denominator b, but numerator a plus b. So there we are. Every fraction gives two children. In fact, you can see the left child is going to be a fraction smaller than 1, and the right child is going to be a fraction bigger than 1. So start with 1/1 and off you go. A left child, a right child, smaller than 1, bigger than 1. A left child, a right child, smaller than 1, bigger than 1. Again, left and right, smaller than 1, bigger than 1, and off we go. A beautiful tree emerges. It's just lovely. And you stare at this for a while and you start to notice things. For example, it looks like all the integers appear on the right path of this tree. And all the basic unit fractions, 1/2, 1/3, 1/4, 1/5 appear on the left side of the tree. That makes sense. You can see why that's happening. But stare at this some more and you look at this and say, ooh, it looks like all the fractions here are distinct. I don't see any repeats so far. And I'm wondering if we're missing any fractions. So here's a question. For example, will the fraction, say, 13/20ths eventually appear on the tree? Can you keep drawing it until you see the fraction 13/20ths? Does it appear? And if so, does it appear exactly once? Or could it appear more than once? For example, maybe you go down here and get to 13/20ths, and maybe you go down a different path and get to 13/20ths down there. Could the same fraction appear more than once in this tree? Also, you look at these fractions and you see they all seem to be in reduced form. For example, I do see 2/3, but I'm not seeing something like 4/6, which is the same fraction, but 2/3 is the reduced form of 4/6. Must every fraction that appears in this tree be in reduced form? Okay, so there are some really cool questions. That's going to be the focus of this particular video, plus more. There are many astounding properties about the fractions in this tree. But let me give it away right now. It does turn out each and every fraction does appear in this tree exactly once and in reduced form, which is amazing. There's no repeats, everything you see is reduced form, and each and every fraction appears exactly once. So let me prove that next for you, and then we'll go through some more remarkable properties of this tree. Okay, here are two numbers, 84 and 120, chosen quite randomly. And I'm going to play a little game of sorts with these two numbers. I'm going to change this pair of numbers as follows. The rule is to keep the small of the two the same. So 84 is the smallest one, don't change it, keep it as 84. But do change the bigger of the two numbers by subtracting the smaller one from it. So 120 take away 84, that's a difference of 36. I'll change the 120 to a 36. That's the game. Not very exciting, I admit, but there's the game. That is, keep the smaller of the two numbers the same, 36, and change the bigger one by subtracting the smaller from it. 84 take away 36 is 48. Great. And I'm going to play this game over and over and over again until I'm about to hit 0 or something negative. I don't want to go to the zeros, I don't want to go to negatives. Avoid zeros and negatives. Stop just before that. Alright, so that's the game. Keep everything positive whole numbers. So what happens if I keep playing this exciting game? Well, right now I've got 36 and 48. Keep the smaller one the same, keep 36 the same, and change the bigger one by subtracting the smaller from it. That's a difference of 12. Great. Now 12 is the small number. Keep that one the same, change the bigger one by subtracting the smaller from it. 24. Do it again, keep the 12 the same, the smaller one, change the bigger one by subtracting the smaller from it. 24 take away 12 is another 12. Oh, and if I keep going, I'm going to be hitting zeros. 12 take away 12 is 0. Stop just before I hit zeros or negatives. So I've got a common value of 12 here. Alright, so here's my question. What's that common value 12 got to do with the original two numbers of 84 and 120? Think about it for a while. Okay, alright, 12, 84, 120. Well, 120 is certainly a multiple of 12. And actually 84 is a multiple of 12. It's 7 times 12. So actually 12 is a common factor of the two original numbers. And if you think along those lines, you might realize after a little moment that actually more than that, 12 is the greatest common factor of the original two numbers. Whoa, and that's not coincidence. Some fellow 2,300 years ago, Euclid, actually figured this out. If you play this little subtraction game of repeatedly subtracting the smaller number from the larger over and over and over again until you reach a common value, that common value is guaranteed to be the greatest common factor of the original two numbers. It's called the Euclidean Algorithm. So let me explain why that's so. Why does that work? So what are we doing here? We take two numbers A and B and we play a little subtraction game. Maybe it's A minus B and B, or maybe it's the other way around. Keep playing a little subtraction game over and over and over again until you reach a common value D and D. Don't go to the zeros, don't go to the negatives. Great. So the question is, why is this common value of D guaranteed to be the greatest common factor of A and B? All right, so here's one way to think about it. Let's just play with common factors first. Suppose 5 is a factor of A and 5 is a factor of B. So 5 is a common factor. So A and B are multiples of 5. Well, they do subtracting of multiples of 5. The difference of 2 multiples of 5 is still a multiple of 5 and still a multiple of 5. If I do some more subtraction, still a multiple of 5, still a multiple of 5. Do some more subtraction, still a multiple of 5, still a multiple of 5. Everything is staying within the multiples of 5. So I keep going, and all I'm doing is subtraction. Everything's staying in the multiples of 5. That must be a multiple of 5. That must be a multiple of 5. That is, 5 is a common factor of D. Oh, if 5 is a common factor of A and B, 5 is a common factor of D. Well, 5 is a factor of D. If A and B are both multiples of 12, okay, still within the multiples of 12. Multiple of 12. Everything's multiple of 12s. Everything's multiple of 12s. Everything's multiple of 12s. Everything's multiples of 12. 12 must be a factor of D. Any common factor of A and B is a factor of D. Okay, that's worthy noting because I wrote it down. I thought that was worthy of noting there. Okay, let's go a little bit further. Can we get something about biggest common factors or something else going on? Well, that was me thinking forwards. What if I played this game backwards? What if I asked, where could this have come from? So one of these numbers was the same. Maybe the bottom was the same. So the question is, what's this number here? Something take away D gave me D. And you realize, oh, that's going to be 2 Ds. Okay, all right, then you ask, okay, where could something like that come from? I'm going to make a choice here. Maybe the 2D stayed the same this time. And now I'm actually doing something take away 2D gave me a D. This must be 3D. Actually, what I'm really doing is adding the 3D there, 2Ds there, adding the 3Ds there. Going backwards is really playing addition. I'm doing lots of additions. Oh, I'm starting with D and D. I'm doing lots of additions of Ds. Everything's going to stay multiples of D. If I keep going backwards, I'm just doing lots of additions all the way through. And this means, oh, this is a multiple of D, and this is something times D as well. That's also a multiple of D. Start with 2Ds and doing a bunch of additions. I must be staying within multiples of D. So actually, D is a common factor of A and B. D is a common factor of A and B. D is a common factor of A and B, and any other factor is a factor of D, which means any other factor is certainly smaller than D. D is indeed the greatest common factor of A and B. There's the Euclidean algorithm. We've just established it right there. Start with any two numbers, keep playing this game of subtraction, take the biggest number from the smaller over and over again, you will end up with a common value which must be the greatest common factor of the two original numbers. It is just beautiful. Love it. Okay, but what's this got to do with the tree? In the early part of the video I was asking about 13/20ths, I believe. Must the fraction 13/20ths appear in the tree? Right, so let's just think through. If it did appear in the tree, what can I say about it? Well, I know it's going to be a left child of something because it's a fraction smaller than 1. So it must come from the left of some parent. And what would the parent be? Well, the parent has the same numerator, so it must be 13 here. And the denominator is A plus B. So 13 plus something gave me 20. So this must be 7. Oh, that's the difference of 20 and 13. Okay, all right, let me keep going. 13/7. That's a number bigger than 1. So it must be a right child of something. Same denominator, so it must be 7. And something plus 7 makes 13. 6. That's the difference. This feels like the Euclidean algorithm. In fact, actually, let me do the Euclidean algorithm on those two numbers, 13 and 20. 13 and 20. I know as I play this game, and I will play the game, I must end up with the greatest common factor of 13 and 20, which is 1. I must end up with a common factor of 1 and 1. Great. All right, so if I do this, keep the smaller number the same and do the difference. 20 take away 13 is 7. 13/7. I do it again. Keep the smaller number the same, 7, and do the difference, 6. There it is. Keep the smaller number the same, 6, and 7 is replaced by the difference, which is 7 takes 6 is 1. Keep the smaller number the same, replaced by the difference, 5. Keep the smaller number the same, replaced by the difference, 4. Keep the smaller number the same, replaced by the difference, 3. Keep the smaller number the same, 1, replaced by the difference, 2. And bingo, that's it, that's correct. Whoa, whoa. In fact, imagine I'm marching backwards through the tree. It's precisely this path of the Euclidean algorithm. And I know the Euclidean algorithm is going to end up with 1, 1, which means actually I could do this process and I know I must end up at 1, 1. I must end up at the apex of the tree, which means if I now read it backwards, 1, 1 must indeed lead to 13/20ths. It must appear in the tree. In fact, there's the path. It's the Euclidean algorithm path backwards. Whoa. Yes, the fraction 13/20 does appear in the tree. In fact, any fraction in reduced form, a, b, if I've got a fraction in reduced form, I know the greatest common factor is 1. So actually, if I did this, if I marched my way through the Euclidean algorithm, I know I must end up with 1 over 1, which means, yes, it appears in the tree. Follow the path backwards. There it is. You'll get to the fraction a over b. Every fraction in reduced form does appear in the tree. Love it. Love it. Now, the next question is, might a fraction appear more than once? Okay, so let's ask that. Could a fraction appear more than once? All right, so say 13/20 appears somewhere in the tree over here and somewhere in the tree over here as well. Okay, it appears twice. That means its parent must also appear twice. Yeah, because it's clear what the parent has to be. You know it's a left child, and you know exactly where it must have come from then. Then its parent must appear twice. So it's a grandparent. Its grandparent appears twice. Its great-grandparent must appear twice. Its great-great-great-great-great, I've lost greats. That generation of parent must appear twice. In fact, you know, this is just the Euclidean algorithm. That means eventually 1/1 will have to appear twice. Because you know it's leading to 1/1. But the thing is, 1/1 doesn't appear twice. That's a contradiction. If 13/20 appear twice in the tree, then 1/1 appears twice in the tree. Not happening. Only way out of that pickle is, I guess 13/20 appears only once in the tree. That's it. Every reduced fraction does appear in this tree, and it appears in the tree precisely once. Love it. Grand and good. And no non-reduced fractions will appear, because you know if you do it backwards, if you have a non-reduced fraction, you'll go back to the greatest common factor of the two fractions. I'm not seeing 2/2 up here. I'm not seeing 3/3 up here. I'm not seeing any non-reduced versions of 1, in which case I know no reduced fraction, non-reduced fraction will appear in this tree either. I think we've clinched it all. We've got it all. Love it. But, as I said, there's much more to this tree. A few years ago, Lionel Ponton made a stunning observation. He realized you can use the tree to prove that certain numbers like the square root of 2 cannot be fractions. They must be irrational. And the idea is this. If the square root of 2 were a fraction, then it must appear somewhere in the tree, because the tree contains every possible fraction. But if the square root of 2 is in the tree, something weird and wrong goes on. Therefore, square root of 2 cannot appear in the tree. Therefore, the square root of 2 cannot be a fraction. It must be irrational. So let me explain the reason behind that. Now, to get there, let me look at the generating rules for the tree, but let me rewrite them, because right now things are a bit weird. I've got a fraction a over b, then I split the fraction up in weird ways. But what's it doing to the actual number itself, the fraction a over b? So let me focus on this. Let's give the fraction a name. Let's call x the fraction a over b. What are these rules actually doing to the number x itself? Well, if I look at the left child and the right child, I'll do the left child first. I want to see if I can rewrite that strange rule in terms of x, the fraction a over b. So let me divide the top line by b and the bottom line by b. Because if I do that, I see the top line is now a over b, the original number x, and the bottom line is a over b, original number x again, plus b over b, 1. So actually the left child is actually x over x plus 1. So I can see what the left child is in terms of the original number. Great, it's that fraction. And the right child is, let's just divide everything by b, because I can see this is really just a over b plus b over b, 1. It's actually the original number x plus 1. All right, so now I can see what the generating rules are doing to actual numbers. Given an actual number x, the left child is x over x plus 1, and the right child is x plus 1. So there's the tree in terms of the original fractions you were working with. All right, so let's see what goes weird and wrong if square root of 2 was in the tree. Square root of 2 is a fraction. So the square root of 2, let's start with it, root 2. Let me start looking at some of its children if it's in the tree. Let me look at its right child first. The right child would be just the original number plus 1. Okay, root 2 plus 1. Now let me look at its left child. Its left child is that number, root 2 plus 1, over root 2 plus 1 plus another 1. So it's actually root 2 plus 1 over root 2 plus 1 plus 1, 2. All right, let me see if I can simplify that on the side. Let me do it over here. So root 2 plus 1 over root 2 plus 2. I don't like all the roots within the fraction parts of the fraction, so let me multiply by the conjugate. Multiply the top and bottom by 2 minus root 2. 2 minus root 2. Whoops, too many things going on here. 2 minus root 2. Okay, scrawly, but here goes. On the bottom, I get 4, take away 2. I get 2 on the bottom. On the top, I get, let's do the integer part. 1 times 2, that's 2, take away 2. Okay, so I get no integer part, and I get, what do I get? I get 2 root 2's, take away 1 root 2. I get just a single root 2 on the top. Oh, this is actually 1 over root 2. Oh, this is just 1 over root 2. It's not too bad. Great, great, all right. Let me now do the left child of that. The left child of that. So let's remove the scratch work. Now I'll do a left child. Left child is the original number over the original number plus 1. So it's 1 over root 2 over 1 over root 2 plus 1. Okay, I can multiply top and bottom by root 2. This is actually really 1 over 1 plus root 2. Great. And now let me do a right child of that. That'll be 1 over 1 plus root 2 plus 1 plus 1. And let me play with this. So this is really 1 over 1 plus root 2 plus 1 plus root 2 over 1 plus root 2. So that of plus 1 plus root 2. Okay, great. Which is really root 2 plus 2 over root 2 plus 1, which looks awfully familiar. It's actually the upside down version of that, in which case it equals the upside down version of this. This equals root 2. Oh, if root 2 appears in the tree once, then it's going to appear in the tree more than once. We know that never happens. No fraction appears in the tree more than once. Therefore, root 2 cannot be a fraction because it can't be in the tree. This never happens in the tree. Root 2 can't be part of the tree. Root 2 is not a fraction. That does it. Whoa, that's just lovely. Okay, so here's the beautiful Calkin-Wilf tree in full glorious form. You'll love it. And we know that each and every fraction appears in this tree in reduced form. Oh, which means actually then, quite remarkable, I can actually read off the fraction. I can go left to right, row by row, start at the top and work my way down. That means I write a list of all the fractions. I'm literally getting a list of all the fractions. You can put all the fractions on the list, and the list begins like this. There it is. So this is the set of all the positive fractions written in reduced form right there. In fact, let me give some notation. Let me call the nth term of this sequence the nth fraction. So here's a list of all the fractions. I'll use Fn to note the nth fraction in this list. Grand. But you look at this list, you start to notice things. For example, I see a pair of 1s there, a pair of 2s there, a pair of 1s, a pair of 3s, a pair of 2s, 3s, 1s, 4s, 3s, 5s. It looks like the denominator of 1 always equals the numerator of the next, all the way through. Now that makes sense. For example, like here, if I've got two children of the same parent, I see that 3 there matches that 3 there, which makes perfect sense because I see the denominator here doesn't match the numerator there. But what's weird, that seems to be happening across children as well. Like this numerator here happens to match that denominator there matches that numerator there. Again, across children. Again, across children. I mean, is that obvious? Well, actually it is. If you just go a little bit further with this tree, for example, we're saying if I now start going across children, so I want to say the right child here and the left child here. So let me work out what the right child there is versus the left child there. Well, let's see, a right child has the same denominator, which will be a plus b and something on top. Oh, here the left child has the same numerator, which would be a plus b and whatever it is on top. So yes, actually right there, denominator matches numerator across children. Great. And the other place it works actually is across the rows. For example, this denominator here of 1 actually matches, with 3 1s, matches that numerator of 1 over here, 1/4. Oh, so it even works across rows, which makes sense. You can see that on the right, each row ends with some number over 1, a fraction over 1, a fraction over 1, a fraction over 1, always denominator 1. And you can check that on the left side of this tree, every row begins with 1 over something, 1 over something, 1 over something, numerators of 1. So actually, this is even working across the rows. So yes, all through this sequence, denominator of 1 matches the numerator of the next. Grand and beautiful. All right, so which means we've really got all the numerators here, that sequence there is appearing as denominators as well. In fact, I can see that. In fact, the denominators are just the numerator sequence shifted by 1. In fact, let's play with that sequence of numerators and hence denominators. So let me call that sequence, I don't know, En or something. The sequence of numerators begins 1, 1, 2, 1, 3, 2, 3, 1, 4, 3, 5, 2. If you kept going, you get 5, 3, 4, 1, and so on and so on and so on. That's as much as I have in my head. Which means the nth fraction is actually given by that nth numerator and the next denominator, En plus 1, because the numerator of the next term is the denominator of the one I want. Got it. So there is sort of a formula for the nth fraction in our sequence if I know a formula for the nth numerator. Great. All right. Lots of amazing things to notice here. For example, I can see the reason I went further here, like I've got between these two ones, 1, 2, 1. Between these two ones, I've got 1, 3, 2, 3, 1. Between these ones, I've got 1, 4, 3, 5, 2, 4, 3, 1. Palindromes. Between every pair of ones, it looks like we have a palindrome. Pretty empty palindrome right there, but it is kind of palindromic. Between every pair of ones, between every pair of numerators of 1, we seem to have palindromes for the numerators. Whoa, is that true? Is that really true? More is true. More seems to be going on. For example, look at every second term of the numerators. Second term. Skip counting through the numerators. And look, you get the sequence 1, 1, 2, 1, 3, 2, 3, 1. 1, 1, 2, 1, 3, 2, 3, 1. It looks like we're getting exactly the same sequence again. That the numerator in the second position is actually the same as the numerator in the nth position. Whoa. Whoa. So I've got the question about palindromes. Is that really true? Palindromes. Is it really close that every term in the second spot is really just the same as in the nth spot? 2nth spot the same as the nth spot? And then we look at that, you can't help but to think, okay, what's going on with the odd positioned terms? And look at this 5. It equals 2 plus 3. Look at this 5. It equals 3 plus 2. Look at this 4 equals 1 plus 3. This 3 equals 2 plus 1. This 3 equals 2 plus 1. This 2 equals 1 plus 1. Is every term in an odd position just the sum of its two neighbors? E of 2n plus E of 2n plus 2? Whoa, there's a third question. There's a lot of structure going on in these numerators from the Calkin-Wilf tree. Wow, wow. So I think we want to play with this sequence some more. Let's do it. Okay, here's a curious way to generate a tree of all the counting numbers. Start with the number 1. It's going to have two children. One child is going to be its double, the other is going to be its double plus 1, 3. They have two children. Each has two children, the double 4 and double plus 1, double 6 and double plus 1, and so on and so on. I claim this process of taking a counting number, giving it two children, its double and its double plus 1, will actually generate all the counting numbers in a tree. And you kind of see why that's going to be the case. I mean, right now you see I've definitely got a power of 2 here, and in fact I've got all the numbers up to the next power of 2, but not including it. But if I were to double all these, do all their left children, just double, I will definitely get the next power of 2, that's for sure, and I'll get numbers just below the following power of 2 after that, so it's grand. But then their right children will be adding 1 to all these, 9, 11, 13, and 15, that fills in all the gaps. And you can see this is 1 less than the next power of 2. Doubling adding 1 is again 1 less than the very next power of 2. You can see this process actually does generate the next row of numbers from the next power of 2 all the way up to the next one. Great. So this will actually generate all the counting numbers this way. But these are also the position numbers of my sequence. That was in the Calkin-Wilf tree. That was our first fraction, place of the second fraction, place of the third fraction, place of the fourth, fifth, sixth, seventh. So that's actually the places of all the fractions in our list. So, let me now draw the tree again with their location numbers, this diagram on top of it. So back in a moment, need to make some space. Okay, so here's the start of the Calkin-Wilf tree with the position numbers located in. For example, the third fraction in our sequence really is 2 over 1. The fifth fraction in our sequence really is 3 over 2, and so on and so on, and keep going down the tree. Alright, so what I'm seeing here actually is that the nth fraction in our sequence is in some position. It has two children, but the two children will be the fractions in position 2n in our sequence and position 2n plus 1 in our sequence. Great. So that now links where the particular fractions are in our list of fractions. But I also know what the fractions actually are. We know the nth fraction is given by the nth numerator over the next numerator. Yep. Which means f of 2n is its numerator, e2n, over its next numerator, 2n plus 1. Ditto for this one. Its numerator, 2n plus 1, over its next numerator, 2n plus 2. Great. So far so good. But I know more. I actually know how to get a left child from a given fraction. Remember, it had the same numerator, and its denominator was a plus b. So that's the a, that's the b, so it'll be a over a plus b. It'll be this a, en, over this b, a plus b, en plus 1. And over here, the right child has the same denominator, which is going to be en plus 1, and the numerator is the sum of what I've got, en and en plus 1. And look at this. Look at this. It tells me fascinating things. For example, oh, f of 2n is given by this expression, and it's given by this expression, and everything's reduced fractions, in which case e of 2n and e of n must be the same. The numbers in every second position of the sequence, every number in an even position is actually the same as the number in its original position. That is, if I select every second term of the sequence, I must be getting back to the same sequence. We observed that, and it's true. It wasn't just a coincidence, it's really happening. And more than that, the number in the odd position terms, e2n plus 1, is actually given by a sum of two things, en plus 1. But that's actually not quite the sum of its two neighbors until you realize, oh, en is the same as e of 2n. It's really e of 2n. It's double. And en plus 1, but the same token, it had to be en plus 1, e of 2n plus 2. It's double. Plus e of 2n plus 2. Every term in an odd position is indeed the sum of its two neighbors. Just like we observed. It's actually a fact. There it is, from the structure of the patterns we're seeing in the tree. And then there's the whole palindromes thing. What's going on? Well, it actually makes sense as well, given what we've got. I mean, we do know the sequence does start 1, 1, 2, 1. It's got some palindromes going on. And in fact, we know, oh, this is actually every second term is actually following this same structure. So every second term must have this palindrome going on. And to get to the next, the in-between terms, just add the two neighbors. Oh, this must be a 2, a 3, a 3, and so on. So now I've got 1, 2, 1, 3, 2, 3, 1, a palindrome. And once I've got one palindrome, I know it's spread across all the even terms that will appear, and all the odd terms will sneak in between and maintain the symmetry of the palindrome. Whoa! Actually, these recursion relations insist that the symmetry of palindromes must propagate throughout the entire sequence. It must propagate between the entire sequence. Got a palindrome between two ones, you'll still have a palindromes between any set of ones as you go on. Build up more and more. Wow, what structure. But the fun doesn't stop there. It keeps on going. Okay, we saw in the last section some beginning hints of connections to the powers of 2. Well, it turns out the connections to binary are mighty strong in all this work, and it's just wonderful. Let me ask this very strange question. Let Bn be the number of ways to write a number n in base 2 using the digits 0, 1, and 2. That's unusual. You don't usually get to use the digit 2 in base 2. All right, let's have some fun. For example, let's look at B6. The number of ways to write the number 6 in base 2 if I'm allowed to use 2's all of a sudden. So let me draw a place value chart for base 2. Here goes. There's the 1s, the 2s, the 4s, the 8s, the 16s, and so on. Great. How can I write a 6? Well, normally I would do 1, 4, 1, 2, and 0, 1s. 1, 1, 0 is the one standard way to write 6 in binary. Okay, that's the standard way. Except now I'm allowed to use the digit 2 as well. So instead of having 1, 2, I could replace that with none of those and make it 2 1s instead. Okay, so there's another way, 1, 0, 2. That is indeed 6. Well, instead of having 1, 4, I can replace that with 2 2s. I'm allowed to use the digit 2, let's use it. So 2, 2, I believe is 6. 2 2s and 2 1s, yes, that makes 6. And if you think about this a while, it turns out that's it. There's only 3 ways to write 6 in binary using the digits 0, 1s, and 2. These 3 ways. So B6 equals 3. Grand, good, lots of fun. So have some more fun. Work out some more numbers. For example, if I start with 0, say B0, how many ways to write the number 0 in binary? Well, you just write the digit 0, one way. How many ways to write the number 1? Just write the digit 1, one way. How many ways to write the digit 2, the number 2 in binary, if I'm allowed to use 0, 1s, and 2s? We've got the standard way, 1, 2, and 0, 1s. But if I use the digit 2, there's a second way now. I could do 2 1s. Beautiful. It turns out there's 2 ways here. B3 turns out to be 1 way. B4 turns out to be 3 ways. B5 turns out to be 2 ways. B6 turns out to be 3 ways, as we saw. B7 turns out to be 1 way. B8 turns out to be 4 ways. B9 turns out to be 3 ways. B10 turns out to be 5 ways. Whoa, what are you noticing? 1, 1, 2, 1, 3, 2, 3, 1, da da da. 1, 1, 2, 1, 3, 2, 3, 1, da da da. It seems to match. It seems to match. Except one little annoyance. This is the first numerator, second numerator, third numerator, fourth numerator. We're counting from 1, 2, 3, 4. Here we're counting 0th term, 1st term, 2nd term, 3rd. So we seem to have that index off by 1. But basically, it looks like these binary numbers, these bn's, really do match the numerator numbers, en's, but off by 1. So the question is, do we truly have such a tight connection to binary that actually doing this weird version of binary really is matching the numerators from the fractions of the Calkin-Wilf tree off by index by 1? Small detail. Whoa, that would be amazing if it's true. And guess what? It's true. It's actually true. So how can we see that? Well, the way to do it is this. Okay, we don't certainly have recursion relations that tell me how to generate numbers in the numerator sequence. I've got the first few here. I know what all the even terms are going to be. E2n is the same as the en's. That gives me all more numbers. And all the in-between terms are given by the sums of their neighbors. So actually, once I start the sequence, I can use the recursion relations to generate the entire sequence. Wouldn't it be nice if these bn's satisfied the same recursion relations, except their index is going to be off by 1. A little bit of annoyance there. But they do satisfy the same recursion relations, and since we know it does start off the same way, you can actually check this. Oh, then using those same recursion relations, starting on the same set of numbers, must generate the whole sequence of numbers that matches all the way through. Everything starts matching, use the same rules to keep going, therefore everything matches forever. Yes, these bn's will match the en's if we can prove they have the same recursion relations. Whoa. And you know what? We can do that. We can do that. For example, before I do that, let me point one thing out nice thing about binary. If I've got some number that ends in a 0 in binary, some digits, 0, then I know that number is even. It's going to actually be well, yes, so they're composed of 16s and 8s and 4s and 2s, but not composed of any 1s. So all numbers involved are even, is an even number. So 2n must be something like A, B, C, it'll be an even number in binary. If I delete that 0, I get some other number with that 0 deleted. Well, what would it be? Well, saying, oh, C was using 2s, let's use half the values. B was using 4s, let's use half the values. A was using 8s, let's use half the values. This actually gives me the number that represents half that, n. So deleting a 0 from a number that ends in a 0 in binary gives me half that number. Okay, that's great. And it works both ways. Bput a 0 at the end of a number must give me double the number. Let me play with that because that will help us out understand the recursion relations for the b's. Let's start with an odd one, b2n plus 1. I have to write an odd number in binary using the digits 0s, 1s, and 2s. I want an odd number. Okay, well, all these are even, so I've got to use the 1. I've got to use the 1 to get an odd number. This can either be 0, 1, or 2 of them. Well, 0 of them means I'm not using it. 2 of them is not helpful. It's going to keep me even. I know if I'm trying to represent an odd number in binary using the digits 0, 1, and 2, I have to have a 1 there. No choice about it. Which means the rest of this number must be up here representing 2n. So I'm going to actually represent 2n in the rest of the picture. Okay. Oh, representing 2n in the rest of the picture is the same as representing n in the picture 1 down, by what I was reasoning before. If I halved everything here, it's the same as representing n in the first part of the picture. Oh, this is the same as trying to represent bn, representing the number n in the first part of the picture. So actually, the odd terms here must basically be half of them. Whoa. And how would I represent an even number like 2n? What are my options here? So if I'm trying to represent an even number, I've actually got 2 choices. Okay, I could use no 1s and just try to get 2n all the way through there, which is really the same as, if I shift it down, it's really the same as all the ways to get n, the number n represented here. Or I could use a 2 there, okay, in which case I'm trying to represent 2n minus 2 in this part of the picture. But if I shift it all the way down by 1, that's the same as trying to represent half of it, n minus 1 in that picture. Whoa! I claim these are the recursion relations e2n equals en, and e2n plus 1 equals en plus 1 in disguise. That, in fact, just shifted by 1, index off by 1. Can we see that? The answer is yes. Here goes. How do we see that? All right, to really see that these relations are matching up with an index off by 1, let me really focus on these ones with the +1 really spelled out. In fact, let me go on this one. It's got lots of +1s already in it. I'm seeing that e of 2n plus 1 is really e of, well, I want a +1 in here, so let's make it n minus 1 plus 1 plus e of n plus 1. I'm seeing e of 2n plus 1 equals e of n plus 1 plus e of n minus 1 plus 1. Yes, that's really this recursion relation with the index off by 1. Great. For this one, let me actually do this. Let me be sneaky. Let's do e to 2n plus 2 is e of 2 is n plus 1, because that gives me a +1 at least on that part. It's the same thing. Except now think of this as 2n plus 1 plus an extra 1. So I'm really saying e of 2n plus 1 with an extra 1 plus 1 equals e of n plus 1. Yes, this really is that recursion relation. Yes, these recursion relations are actually matching up this way. The index is off by 1. Whoa! Both sequences start off the same way. Both sequences use the same recursion relations to generate every other number of the sequence. Therefore, every number of all the numbers in the sequences match completely. Bingo, beautiful. This is stunning. This is amazing. And in fact, here's the crazy thing. Here's the astounding fact. If we take this sequence of numbers that you say, these are really coming from counting binary in a strange way, then those sequence of numbers have the amazing property that every consecutive pair of numbers represents a reduced fraction, and every reduced fraction that could possibly occur does occur. Whoa! If you had to try to prove that just by thinking about binary, writing numbers in binary with the digits 0, 1, and 2, I don't know how you'd go about it. But seeing this connection to the fraction tree makes this clear to us now. Yes, because we know the numerator of 1 is the denominator of the next, and so forth, and so on, and so on, and so on. Sorry, the denominator of 1 is the numerator of the next. These really do represent each and every pair of fractions in reduced form. Yes, this weird way of counting in binary has this amazing number theoretic property. Whoa, astounding. And the connection to binary doesn't stop. It is astounding. Here is the counting numbers in a tree superimposed over the Calkin-Wilf tree. All the fractions there beautifully connected here. So let's look at, say, the 13th fraction. It's 5/3. 5/3. But here's the weird thing. Write the number 13 in binary using digits 0 and 1 this time. It's 1, 1, 0, 1. We've got a block of 2 1s, 1 0, and 1 1. I claim if you write this funny fraction, 1 plus 1 over 1 plus 1 over 2. Unravel that. That's 1 plus 1 over 3 halves. That's 1 plus 2/3. That's actually 5/3. It's that fraction. What happened? Let's do it again. 9. I'll choose the ninth number. 9. Right in binary. 9 is 8, 0, 0, 1. So that's 8, 4, 2, 1. Yes, 9. That's it. I see 1, 1, 2 zeros, and 1, 1. So let's read this backwards and create this crazy fraction. 1 plus 1 over 2 plus 1 over 1. Let's unravel that. That's 1 plus 1/3. 1 plus 1/3 is 4/3. And that is indeed the fraction of the ninth position. Whoa! So it's a little bit strange if you choose an even number. I'll do that. Let's choose, say, 14. 14 is the fraction 4/3. And 14 in binary is an 8, it's a 4, it's a 0, it's a 4, it's a 2, 8, 4, 2, if I can do my, 2 and 0. There we go. I actually want to count blocks that begin with 1s and also end with 1s. I've really got no 1s at the end. So I think it's the block as 3 1s, 1 0, and 0 1s. All right, because if I do that and use the strange backwards way of writing a fraction, 0 plus 1 over 1 plus 1 over 3. If I do that, I get 1 over 4/3. Yes, I get 3/4. In general, if n is given by some 1s and some 0s and some 1s and some 0s and some 1s, so I'll do P, Q, R, S, T, and it could be no 1s at the very end, in which case T would be 0, like the 14 case, then I claim the nth fraction is actually given by this weird thing. Start backwards. T plus 1 over S plus 1 over R plus 1 over Q plus 1 over P. Or if you need a longer one, keep going. That is the nth fraction in the tree. You can read it off from the binary expression of its position. Whoa! Why does that work? What's going on there? That is insane and fabulous. Let's talk about it. Okay, so why might this be true throughout the entire tree? Now, yes, you check it's true for all the fractions at the top of the tree. Just do that by hand. But then the thing is, if you know it's true at one level, could we then argue it must be true for the children of that fraction as well? In which case, truth here is propagated to the children, which is propagated to the grandchildren, be propagated throughout the entire tree. So what we really need to do is say, okay, we can check by hand it's happening for the top fractions. Therefore, can we now check, if we know it's true for one fraction, must be true for the children, then we're golden. And then we're golden. So let me do it here. Suppose we've got some position number n. I've just done 3 blocks here, just to make my life a little bit easier. A block of 1s, a block of 0s, a block of 1s, r of them, q of them, p of them. So there's the number in binary. And we know if it's true that it's the fraction in the nth position is then going to be given by this weird p plus 1 over q plus 1 over r. If I know that's true, can I then say the same thing must be true for its left child and its right child? So let's see if the same pattern's holding here and here. All right, so I have a feeling it's going to take a lot of work. So I'll do the left child first, and probably have to do a lot of erasing and then do the right child second. But we know the left child is in position 2n. And we know that position is given by putting a 0 at the end of this binary expression. So I'll have a whole bunch of 1s, r of them still. A whole bunch of 0s, I'll have a q of them. I'll have a whole bunch of 1s, p of them. And then I'll have a 0 at the end, which is just going to be one of them. Except we want the block to end with some 1s again, even if there's none of them. So actually 0, 1, 0 ends in 1, 0. Which means the fraction we're going to associate with this is 0 plus 1 over 1 plus 1 over p plus 1 over q plus 1 over r. Whoa. Whoa. Okay. That's the fraction, which we know is, oh, look at this. P plus 1 over q plus 1 over r. This part here is the original fraction a over b. So this was, don't bother about 0. This is 0 plus 1 over 1 plus 1 over the original fraction, a over b. Multiply top and bottom by b, I get, well no, let's actually unravel this first. This is 1 plus b over a, multiply top and bottom by a, this is a over a plus b, which is indeed the correct left child. This is indeed going to be a over a plus b, that is going to be the correct left child, f of 2n. Yes, yes, that pattern's working here. One little caveat. If I had 0 1s here, you have to actually adjust things a little bit here, what I've done here, and check it still works. It actually is working in the case of the 0 1s there. All is grand and good, it'll work out. And for the right child, okay, so truth happens for, if it's truth happening for a parent, it's happening for the left child, is truth happening for the right child as well? Let's find out. Well, in this case, we know that the position of the right child is 2n plus 1. So it'll be the same binary number, 0, 0, 0, 1, 1, 1, with an extra 1. So we've got p plus 1 there, q zeros, and r 1s. Which means the fraction I'm associating with here is p plus 1 plus 1 over q plus 1 over r. Which is 1 plus p 1 plus p plus 1 over q. It's 1 over the fraction I had before. It's 1 plus a over b, which is indeed a plus b over b. That's the correct right child. Yes, I do indeed have the correct right child fraction right there. It must be true that it equals that. So truth at one level is going to be propagated to all children and will hold all the way through. This is beautiful, and there it is. What connections to binary? It is mind-blowing.